Welcome to the lab on locating the epicenter of an earthquake. It's actually more, that's a short version of it. What you need to do is open up the virtual earthquake website, which I've already done, so we're going to have two windows open. There's a lot here, and I'm not going to spend your time reading it to you. That's always kind of irritating. On occasion, teachers will do it because they want to make sure you really know it. I want you to know it, but in an online course, you want to read this yourself. Couple of things to emphasize. P waves travel faster than S waves. P waves, think of Usain Bolt. S waves, think of you. You're both at the starting line. Let's say you're running the 200-meter dash. You both take off. Who's going to get to the finish line first? Probably Usain Bolt. He's the fastest guy in the world. You, the S wave, you'll arrive there a little bit later. Now, the longer the race is, the sooner Usain is going to arrive at the finish line than you. If it's a 5-meter dash, you may be 1 second behind. If it's a 400-meter dash, you may be 10 seconds behind, but the longer the run, the greater the lag time between you. It's the same way with P waves and S waves. Now, enough talk, let's start working. There are 4 different earthquakes that we are going to fill in information on. You're going to calculate the SP interval in seconds for the San Francisco earthquake. In order to locate an earthquake, you need 3 sets of data. Remember the triangulation I talked about from the lecture notes? In the case of the San Francisco earthquake, we have stations in Eureka, California, great little town, Elko, Nevada, no comma, got to put that in there, and Las Vegas, Nevada. Dang, I did not type well. By the time you see this, everything will be kind of perfect. You're then going to convert your SP interval into the epicenter distance, and then you're going to figure out the Richter magnitude. I misspelled Richter. Oh well, I was rushing through this. You're going to do the same thing for Southern California, Japan, and Mexico. I love some of these names, Akita and Chihuahua. Okay, let's move on. Let's do the San Francisco area earthquake. I'm going to click on Submit Choice. You, when you get around to this, are going to go back and click Southern California, Japan, and Mexico, and do all 3 of those by clicking Submit Choice. But right now, I'm going to do this one for you, and you can fill in the data while watching. Here is a sample seismograph. I am going to hit Command plus to zoom in. On the PC, I think it's Control plus or something like that. Here's the time in seconds. Here's the millimeters of deviation from the standard that the little stylus or pen wiggled on an old seismograph. Here's the arrival of the P wave at 0, and thankfully these guys have always moved the P time to 0. It's not really that way. And here's the arrival of the S wave. Let me shrink this back down to normal size. So, a simulated earthquake has occurred somewhere on this map. We have a seismogram from the Eureka, California station, the Elko, Nevada station, and the Las Vegas, Nevada station. Let me zoom in again to make these bigger. We have to figure out how many seconds behind the P wave arrival, right there, the S wave came in. We've got 0, 10, 20, 30, 40, 50. Looks like each one of these blue lines is 2 seconds. So, we know it's 40, 42, 44, 46, 48. It's not quite 50 seconds. I'm going to call it 49 seconds. Now, if you're not quite on, the lab will tell you, and you can go back and retry this. Here's the P wave arrival time. Here's the S wave arrival time. To me, it looks like right about 72 seconds. I would go 72.1, but it won't let me do that. It takes only integers, full numbers. For Las Vegas, here's the P wave arrival, and the S wave to me looks like 64 seconds. Okay, I'm going to click the little button that says Convert SP Interval. The little application has taken our times and put them into this data table. We are now going to use this SP distance graph to figure out the epicentral distance, the distance to the epicenter. I'm going to zoom in again. Let's use our data from Eureka, California. The lag time was 49 seconds, so we're going to go up here on the graph to 49 seconds. Now in this case, it looks like each blue line represents 1 second. I'm going to go across 49 seconds until I hit the black line. I'm going to zoom in because I want to be really careful. 49 seconds. I'm thinking, okay, here's 400. If I go over here, hit the black line, and then drop down, some people would say it's 480, but I think the black line crosses maybe a little bit before 480, so I'm going to go 478 kilometers. Let's try Elko, Nevada. Our interval time is 72 seconds. So remember, each one of these is 1 second. So I'm going to go up to 72 right here, go across until I hit the curve, which is straight. Ooh, what do you think about a fourth of the way across? Maybe a fifth? Let's go down. So if each of these is 20, I'm going to say that's 704, 705, I'm not sure. Las Vegas, Nevada, 64 seconds. 61, 2, 3, 4, 64. And I'm going to go down 620 and 6, it's about a third of the way. I'm going to go 627. If these are right, we're going to be told how close we are. Oh, let me go back to normal size. Excellent work. The green circle is the circle from Las Vegas. We know that the earthquake occurred this far away, so if we put a compass point on Las Vegas and draw that distance we got from the previous page, if I go back, by the way, the data won't be there. We can draw a line and we know the earthquake occurred somewhere along that green line. We can do the same thing from Elko. We know it was a long way from Elko. We can put our point of the compass here. We can measure out, whatever it was, 700 and something kilometers, and draw out a circle. And then we can do the same thing for Eureka. Where all three circles cross, that's where the earthquake is. And it looks like we did a really good job. I should let you know, this is unusual. I usually don't do well at these things. Now, your data by this time should be put in here. You could have the data for Eureka, Elko, Las Vegas. You could have the distance. We are now going to calculate the Richter magnitude. All our data from the previous pages are going to be taken and put into the next page. What we're going to look at here is the magnitude of the earthquake. The bigger the earthquake, the more you're going to have wiggleation on this scale. I just made up wiggleation, copyright me. In the case of this earthquake, it looks like you have about 190 millimeters of wiggling. Ah, I was wrong. They said 185. See, I'm not always right. Now, you can read this if you want. We're just going to go to the next page and I'll show you what to do. Let's figure out the amplitude on each of these graphs. What's the biggest shaking we got on this one? There's 200, there's 250, so it looks like each blue line is 10. To 10, 20, 30, oop, 250, 60, 70, 80. I'm going to go about 285 millimeters. The Elko, Nevada, notice the amplitude is a lot less. Why? Elko, Nevada was a long way away. The Eureka, California station was a lot closer. So you get more shaking, and this one is in between. Elko? What do you think? 50, 60, looks like about 60 millimeters of deviation from the norm. And in this case, they made it easy on you. I think it's about 100 millimeters. The biggest deviation is right there, and that's 100 millimeters. Let's see what happens, because the program will automatically put all this data into a graph. They should all cross. Dude, we're good. Where all three of them cross, there's the distance, and there's the amplitude. Here is our magnitude. So here's 8.0, there's 7.5, there's 7. To me, it looks like a 7.1. Confirm magnitude. Cool. Now, if you want, you can enter your name here and it'll email it to you, and then you can email it to me, and it doesn't really matter. But by now, you should have all these data entered into here, and then try it yourself. Again, if you don't get it right, just start over. All you have to do are the Southern California, Japan, and Mexico portions of this. It's really pretty easy, and it's kind of fun. You then have 3 questions to answer. How close were you for each of the quakes? The first time I did this, I had to try it a few times, so don't worry if you have to retry each of these 3 a few times. Explain why a minimum of 3 stations are necessary to locate the epicenter accurately. And here's a crazy question. If P waves and S waves traveled at the same speed, they don't. How would that affect our ability to triangulate earthquakes? Yeah, it's a thought question, but it's still kind of cool. Enjoy! And thanks for watching.